Hi everyone, I'd like to continue on this position, velocity, acceleration example and just really make sure that we specify exactly what I'm getting at here. So if we're looking for acceleration at a specific point in time, we're talking about the instantaneous rate of change of velocity. At that moment, exactly how fast is velocity changing? Which means that acceleration is going to be oh, am I getting ahead of myself? I think so. I'm getting ahead of myself. Okay. So let's say that we have acceleration function named a of t, velocity function named v of t, and position function named s of t. We want to figure out how we would find a of t from v and from s. So if we're starting with velocity, and we want to get acceleration because it is the instantaneous rate of change of velocity, that means we should take the derivative. So the derivative of velocity is acceleration. If we want to start with the position function, if we take the derivative of the position function, what we have is velocity, which is not good enough because we want to get all the way down to acceleration, which means we'll have to take the derivative again. So starting from position, you take the derivative once to get velocity, and then you would just repeat the process on the velocity function to get acceleration. So we'd have to do limit definition twice. Okay, the other thing I want to do in here is looking at the graph. I want to talk not just about the velocity, what am I trying to say? Position, velocity, acceleration piece, but also about the increasing, decrease, the shape of the graph. So the bottom of this page, let me fold so we can see it. We're supposed to compare graphs, and we're supposed to use the words increasing, decreasing, constant. So positive slope, negative slope, slope is 0. Concave up, concave down, and linear. And I think I've used the concave up, concave down before, but if not, concave up looks like it's somewhere on the bend of an upward facing parabola or something along those lines, and concave down, it looks like it's somewhere on a downward facing bend of a parabola. Or linear. Linear has no bend at all, so it doesn't have to be horizontal, but straight line. Okay, so we have these pictures we can look at. Let me see if I can keep this where you can see it. So first we're supposed to compare position and velocity. So the first question is, if we know our velocity is positive, what does that tell us about position? So our velocity is positive other than on this last little stretch from 10 to 14. And as long as velocity is positive, that tells us that our distance is increasing. Our position function is increasing, has positive slopes, which should make sense because that's how we got it, right? The derivative of this is velocity. So when this is increasing, this is positive. If you're feeling comfortable, feel free to pause and fill these out and then just check back in and make sure you had the right idea. If velocity is negative, which we don't actually see in this picture, but that would imply that the slopes here are negative, which means your distance is decreasing. And if velocity is 0, which we do see right here, that tells us that the slope of the position function is 0, which means your distance is constant. Your distance is not changing. On an interval where a is positive, okay, so now we're looking from a to v, so let's hide that. On an interval where a is positive, so say right here 0 to 2, what is happening to velocity? So if a is positive, that means the slopes here are positive, which means, just like before actually, that velocity is increasing. So if acceleration is positive, velocity is increasing. If acceleration is negative, like it is on this little stretch, then your slopes are negative, which means your velocity is decreasing. And if a is 0, which happens on a couple of different stretches, then your velocity function has slope 0, which means your velocity is not changing, so that's constant. Okay, last comparison is S and A. Let's see if I can make this fit. Okay, so there's S and A. Better if I go this way? Maybe. Okay, so now we want to compare the A graph and the S graph. So if A is positive, we want to figure out what's happening to the position function. We've already said positive A means velocity getting bigger, and we saw that right here on this stretch. So what that means is our tangent lines are getting steeper, and that's giving us a concave up shape. If acceleration is negative, that means velocity is getting smaller. So that's right here on this stretch. So on the original function, the slopes are getting smaller, which means it's concave down. And then almost fits. There we go. Last one, if A is 0, so that's from 4 to 8 and from 10 to 14. So let's see, that's this chunk and this chunk. On those intervals, acceleration being 0 means velocity isn't changing. Velocity is constant, which on the original function looks like straight line, or at least close to it behavior here. So it should be perfectly straight line if A really is 0. So yes, this is constant, but this also has 0 acceleration, and it's not constant. The answer to that one is linear. It's not bending. If acceleration is 0, then it's not speeding up or slowing down, and it should look like a straight line. Okay, so one quick thing I want to point out here is there was something really similar happening when we compared S and V, and there was something really similar happening, or I guess I already said that. I'm repeating myself. This was really similar to what was happening when we compared V to A. So what I want you to see is that the reason that's similar is because both of these are one derivative apart. So the slopes of S are given by V, the slopes of V are given by A, which is why we're getting that increasing, decreasing constant for both. The one down below is different because we're comparing S to A, which means we need two derivatives. So whenever, it doesn't matter if it's the function and the derivative or the derivative and the second derivative, you should always be thinking slopes whenever you have things that are a single derivative apart. And then if they're two derivatives apart, you should be thinking about the bend. Is it getting steeper or less steep? Okay, thanks.